here. Is there not a meter stick?
Card?
Ah, thank you. All right, so that is at a position of 8.59 centimeters. Let's see how long that takes to fall. All right, so what did I say? I said
8.59.
85.9 centimeters. That is the position right now. I'm going to stick a 20-gram mass on it. Now, it is lopsided here. Really, to get a proper measurement, I need to probably pick the middle. Now, if this were a lab, I would measure the height of the low spot and the high spot and take the average of the two, but I'm just gonna eyeball it for right now. So that's roughly the middle right there, and that is, and it probably helps if I have the same standard. Well, that other number is wrong, I'll tell you that. Because that is 85.0. The other one was 75. Let's try that one again. Shouldn't have taken it off. All right, I need a rubber band. It's getting too cluttered in here with all the extra stuff, and so cleaned up, the sauce is cleaned up. Now I can't find the stuff when I need it. All right. Trouble is that the numbers I'm going to be getting will be different depending upon the size of how many coils I have loose. And when I took it off there, I changed it. So let's pretend this is going to hold. All right, so with nothing on it, take two. I'm going to use the table as my reference, and let's go ahead and do it with 0 at the bottom. And my place is marked. Some people just can't abide by Slinky's falling. State. All right, so 20.5, like best I can do. All right, so my initial position at the end, 20.5 centimeters. I'm gonna put a 20-gram mass on it, and I will just assume that that 20 grams is accurate. Again, I'm going to use the table as my reference there. Oh, this slipped. Take 3. Welcome back.
Thank you.
stability.
Do you want one of us to help you?
I appreciate the offer. It's all gonna work perfectly now. All right, as I was last saying, the initial distance, along with hair, all right, 14 centimeters. Put the mass on it, and please don't touch the table. Of course. Take 4. You know, what I'm trying to get out of this is gonna take less time than it's actually taking me to get the numbers.
Rejoice.
Yeah, that's it. All right, so now, the inertial position for the 4th time is 30.3 centimeters. I'm going to put a 20-gram mass on it. It is not going to fall. It is not going to touch the table. Everything is going to be beautiful. Come on. There we go. The position is now going for the middle. It's like 19.5. All right, so let's take a look at the forces involved here. I've got a spring that's just hanging naturally. I attach a mass to it. 20-gram mass or 0.02 kilogram mass. What are the forces acting on the mass?
Tension?
It is a tension. We're going to be more specific because we do have an independent formula for it, and it is a conservative force. We have this spring force acting upwards. That spring, so it is in equilibrium. So F, if I make a positive, Fs minus the weight is equal to mass times 0. Still F equals ma, that doesn't go away. The formula for weight, mg. And the spring force, if it is an ideal spring, is that the force is directly proportional to how far it has displaced. And so we use this K, lowercase k, delta x. This K right here, we involved it before when we did an energy problem. This is the spring constant. And in this situation right here, the reason why I had to redo one of them is when it fell, if I had a different number of coils, it'd be a different spring constant. So I have my spring constant times delta x is equal to mg. So if I wanted to solve for my spring constant, I have k is equal to mg over delta x. And then we plug and chug. My mass was 0.02 kilograms, g 9.8 meters per second squared, divided by how far it stretched when I added that weight to it, or the mass to it. Well, how far did it stretch?
10.8.
Say it again?
10.8 centimeters.
Or 0.108 meters. you work through the fancy math, somewhere around 2. A little less than 1.93. So it's not to tell me. 1.81? 815. Units? There are units.
Newtons. Is it newtons?
If you're stopping there, no. If you're gonna continue, could be.
I wasn't gonna continue, so.
But he got the first half, just gonna finish it up for him.
Newton meters?
Oh, so close.
Newton.
There we go.
Per meter?
Newtons per meter. A Newton meter is a very different unit. So what it's claiming is that for every 1.815 newtons, I will stretch it a meter. Now, if any of you have owned a metal slinky before, you know at some point you will stretch it beyond the point where it would bounce back. You will exceed the elastic limit. But we're using this as a model for an ideal spring, and so that's what we can do right there. All right, so we have a spring constant of 1.815. That's sort of a stiffness. If I had a spring of 3 newtons per meter, it takes more force to stretch it a meter, and therefore that would be a stiffer number. So the stiffer spring, so the larger K is, the stiffer the spring is. Now, let's do a little math here. If something is going to obey simple harmonic motion, it obeys what's known as Hooke's law. That the force exerted by the spring is equal to negative K delta X. The negative there tells me that the force from the spring is going to be opposite the displacement. So it has a normal position there. If I pulled it down, that the force the spring exerts is going to be up. If I push it up, the force from the spring is going to be down. So that's the point of the negative, is to indicate that it's opposite the displacement. Over here, I don't have the negative because I already took that into account when I said that the spring force would be up. I know this is going to be equal to mass times acceleration. I'm going to simplify it just a little bit for the sake of the derivation. Displacement, this is the final position minus whatever equilibrium is. I think there's a video I have where I go through a more formal process. Since I can establish, so in essence, if I establish equilibrium to be my 0, my origin, so if I let that be 0, then this is just the position. So negative Kx is equal to MA. It still works even if you kept it more general, but. Now acceleration. What is acceleration?
The change in velocity or the change in time?
All right, so this is mass times the change in velocity over the change in time. What's velocity?
Like the definition?
Yeah, the math definition.
The displacement, the change in displacement over time?
I'm gonna nitpick that. I think you would write it up correctly, but it's not the.
The displacement over time.
There we go, or change in position over time. So this would be mass times the change in time, the change in position over the change in time. Remember that velocity is the slope of my position versus time graph. Acceleration is the slope of my velocity versus time graph. So what this right here is the slope of the slope of my position versus time graph. So I've got position on the right-hand side of my equation here, and I've got position on the left-hand side of my equation. So whatever function I have for position, I know that if I did the slopes of the slopes, I need to have something that kind of looks like position. So the question is, what function, if I did the slope of the slope, would it look kind of like what I started with? And a hint, I've already mentioned it. So we need that. Okay, so let's start out with a parabola. If my position time graph is a parabola, what would my velocity time graph look like? So the hand gesture there, it looked like a straight line. It starts out at around 0, and then my slope gets steeper. In other words, my velocity gets steeper. And then my acceleration versus time graph, slope is constant. So this would not work. My acceleration graph doesn't look like that.
The position over time would have to be a cosine.
If it's a cosine, so there's basically my cosine curve. Keep going. So if that's position versus time, well, my velocity, I know it's the slope, so my 0 here. So this is a cosine curve. 0 there, 0 there, 0 there, 0 there. My slope, positive or negative here? Slopes like that.
Negative.
All right, so it's negative, and then from here to here,
Positive.
and it's going to oscillate back and forth. What is that a graph of?
Negative sign.
If we did it again, so my acceleration versus time graph, well, I know the slope is 0 there, 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 and there. In this first region, my slope positive or negative?
Negative.
And then from here to here, and then oscillates back and forth. Now, it is not exactly what we started with. It's the flip of it. This is a negative cosine, but it's something we can work with. If we found the jerk, not a vector, not a unit vector. So the jerk first time, well, I know it's 0 at the beginning. It's 0 there, and 0, then 0 periodically. This first section, positive or negative?
Positive.
So it's going to oscillate back and forth like that. And what is that a graph of?
Sine.
If I did the snap, what's the snap going to look like?
Cosine.
Yeah. So 0, 0, 0, starts out positive, and oscillates like that, and I end up back where I started. So we get this pattern with trig functions that if I'm doing slopes of slopes, the pattern goes cosine, negative sine, negative cosine, sine, and then back to cosine again. It just loops around. Well, let's take it one step further. And I'm going to need that number again at some point. That was 1.815. Okay. was the spread constant, okay? All right. So if I plotted x equals cosine of t, this would be 2 pi to here. Suppose I did the cosine plotted the cosine of 2t. What does that do? What does sticking a 2 in front do? Doubles what?
Time.
Doubles time? Okay. So what, how would the graph change?
The period would be shorter, no. Yeah,
There'd be more frequent periods.
Okay. So more frequent oscillations, the period is, matter of fact, cut in half. If you imagine that I've got a wheel here with a peg in it, and the wheel is rotating around at some angular speed of omega. As this peg is moving around, I look at a shadow that it casts, let's put the light up here. I look at the shadow that's appearing down here. So the shadow's oscillating back and forth in a cosine function. If I increase the speed, if I double the speed, that point is going to be moving back and forth, be twice as fast as it was the first time.